So next part in our syllabus we are going to look at adsorption and ion exchange. So think about from your undergraduate course where adsorbents are used and where adsorption processes are used, where ion exchange processes are used and where chromatographic processes are used. So if you think about some of the adsorption processes are used to remove impurities. Very commonly they are used to remove coloring impurities from solutions before you crystallize them in pharma products, or for example in when you want to do effluent treatment, some coloring matter goes after the aerobic treatment, you would want to do adsorption to remove the coloring matter. Ion exchange processes are used to remove cations and anions from water. So for water treatment, for example, if you want to make water which is used for boiler feed water, you need to remove all the salts and sodium and sulfate ions. So there you do cation exchange and anion exchange, so that you get water which is essentially free of ions, which is called as demineralized water or deionized water. Some of the pharmaceutical processes also require ultra pure water, so for those kinds of water are also produced by ion exchange. Chromatography, you must have studied about gas chromatography and liquid chromatography. So there you are separating two components by their selective affinity towards the adsorbent. So these are the various places where these processes are used. Also recall from our CRE lectures the following concepts. So for example, we looked at the pore sizes: microporous, mesoporous and macroporous materials. Depending on the size of the pore, they are classified into these different categories. Also recall that surface area per unit mass is very large. That allows us to use small amounts of the adsorbent material and absorb large quantities of material. Recall concept about bulk density and particle density and porosity of these materials. So let's start by looking at some thermodynamic aspects of the adsorption processes. So if you think about some of these typical adsorbents that are used, say activated alumina or silica gel or activated carbon, these molecular sieves are called as zeolites very commonly. Polymeric adsorbents are also there. You can see their nature. Some of them are hydrophilic, some of them are hydrophobic, and you can see the pore sizes that are there. Pore sizes are of the order of 3 angstroms, or so 0.3 nanometers, which will mean that you are able to do molecular level separation based on these zeolites. Some of these could be having large pores. So for example, this is 3 nanometers and more than 3 nanometers. So this is definitely mesoporous materials. Look at some of these particle densities and particle porosities and the corresponding surface area. You can see that some of these materials have very high surface area of the order of 1000 meter square per gram, which means you can use very small amount of the material and you will get very large surface area. You might be using it for catalytic applications or you might be using for adsorption applications. So these zeolites have very uniform pore size, and the pore sizes are of the order of size of the molecule. That allows us to do molecular level separations. For example, paraxylene and let's say metaxylene separation. Some of these polymeric adsorbents could be hydrophobic if they are made from, let's say, styrene and divinyl benzene, and they could be used for adsorption of non-polar compounds. Some of these polymeric adsorbents could also be hydrophilic. For example, if they are made from acrylic esters, then you can be used for adsorption of polar compounds. So depending on the compound that we want to adsorb, we will select different material which could be hydrophilic, hydrophobic, which could have required surface area and a good adsorption capacity, and we will talk about all these things one by one. So first of all, what are the thermodynamic aspects? So if you think about adsorption, if you write delta G as delta H minus T delta S, now because adsorption is occurring, that means delta G is negative. Also delta S, if you see, it is the solute is going from the gas phase or the solution phase into the adsorbent phase. That means the entropy of the solute is reducing. That means this delta S is negative. So that means this whole term becomes positive. If you take it on the other side, it becomes negative. That means delta H is always negative. So that means adsorption is an exothermic process. So if it is an exothermic process, the equilibrium of the adsorption will be favored at lower and lower temperature. So we would want to adsorb materials, adsorb the solute onto the adsorbent at low temperatures, so you get a high equilibrium adsorption. Whereas when we want to regenerate, we would raise the temperature so that the equilibrium is shifted towards the desorption. Also recall that the equilibrium constant you can relate to minus delta G by RT, and if you measure this equilibrium constant at different temperatures, you can work out the heat of adsorption delta H by RT square. So dlnk by dt is delta H by RT square. This is very much like your the basis for Antoine-Clausius-Clapeyron equation. Okay, just some types of adsorption isotherms that are used. First of all, what is an adsorption isotherm? Adsorption isotherm tells you what is the amount adsorbed onto the adsorbent in terms of moles per gram or grams per gram or milligrams per gram, or if it's a gaseous adsorbent, you can represent in terms of the volume of the gas at STP adsorbed per gram of the adsorbent, versus if it's a gas phase, you can represent in terms of pressure. We might want to represent in terms of pressure divided by the saturation pressure or vapor pressure, or if it's a liquid from which adsorption is happening, we could represent this in terms of the concentration of the solute in that solution. So first of all, type 1 adsorption isotherm looks something like this. What this shows that this is obeyed for gases at temperatures more than the critical temperature. What this shows is that the amount adsorbed goes up, and as you increase the pressure, it finally reaches a maximum limit. So this is a good this kind of isotherm is good for adsorption, because even at a low pressure, amount adsorbed is significantly high, and this is very typical of unimolecular adsorption onto the surface area, or what we call as Langmuir adsorption isotherm. We will come to that as we go along. Second type of adsorption isotherm is called as type 2. What it tells is it is a multimolecular adsorption. That means a layer of the substance, layer of the solute is adsorbed, on that layer another layer, and on that layer another layer, so that several layers can be adsorbed onto the surface of the adsorbing material. So this is observed when we have gases which are lower than the critical temperature and pressure approaching the critical pressure. This kind of behavior happens when the heat of adsorption of the first layer is more than the subsequent layers. That means if you think in terms of thermodynamics, what this means is that it is favorable for the first layer to get adsorbed, and the second layer, third layer, and so on and so forth are progressively lesser and lesser favored. But in general, this is good for adsorption, because again you can see that at lower pressure you can get significant amount of adsorption. Type 3 is also multimolecular adsorption, which means multi-layer adsorption. In this particular case, heat of adsorption of the first layer is less than the subsequent layer. That means it is unfavorable for the first layer to get adsorbed. The second layer is more favorably adsorbed onto the first layer than the first layer getting adsorbed onto the adsorbent. This is undesirable for adsorption, because the first layer itself does not get loaded till high values of pressure, so the amount adsorbed is less for a significant amount of pressure. There are two more types, type 4 and type 5. Type 4 is like type 2 and type 5 is like type 3. Now type 4 if you see and type 5 if you see, both of them exhibit hysteresis, meaning that if we increase pressure and the amount adsorbed, if we keep on tracking, the amount adsorbed increases in this manner. But now if we start reducing the pressure, it does not trace back the original path, but it traces a different path like this. Same way here, while increasing the pressure, it follows this path, while reducing the pressure, it follows this path. So this shows clearly that hysteresis occurs, and this hysteresis is very characteristic of condensation of the adsorbing material inside the capillaries or inside the pores of this. So condensation can occur at a pressure even less than the saturation pressure. So because of that, the maximum capacity is reached even when the pressure is less than P0. That means, because if it is condensing, the amount that can be adsorbed, the volume that is of the of the solute that is there, even in a small volume, if it's a liquid phase that is there present inside the pore, the amount can be very large because density of the liquid is large as compared to density of the gas. In your thermo course, you must have studied how the fugacity and the vapor pressure inside pore and inside and in the bulk of the phenomena is related. So recall from those lectures, I am just giving you the final expression. So if you see Psat, the saturation pressure or vapor pressure inside the pore divided by vapor pressure in the bulk of the material is related to this term e raised to 4 gamma cos theta, pore diameter, liquid molar volume and RT. This is like your Poynting correction factor, and this is the capillary pressure, the increase in fugacity due to the capillary pressure. So if you think about this for a liquid, let's say liquid nitrogen is at 77 Kelvin, 1 atmospheric pressure, that's the boiling point, so vapor pressure is 1 atmosphere. If you think in terms of a 3 nanometer pore, let's say surface tension is 0.01 Newton per meter, VL is 34 centimeter cube per gram mole, then you will find that Psat inside the pore divided by Psat is about 0.5. That means condensation at this particular temperature, condensation can occur even when pressure is less than is about 0.5 of the vapor pressure. That means, so you can see that here condensation has occurred and suddenly the amount adsorbed increases because the liquid has gone inside the pore. Large amount of liquid gets large mass of the substance goes inside the pore because it is present in the liquid form. So these are important when we try to adsorb and desorb the material, when we want to regenerate the material. So you need to trace the whole adsorption as well as the desorption curve to identify whether this kind of phenomena is happening or not happening. We'll just very quickly look at some of the adsorption isotherms. So for example, if you want to think about type 1 monolayer adsorption, it also means that there is no preferential site for the solute onto the adsorbing material. All the sites are equally favorable for the solute to get adsorbed. Now if we what we did in our catalysis course was try to look at it as a vacant site and balance and a reaction between something in the gas phase, solute in the gas phase, and the vacant site on the adsorbent material. So here we try to represent that vacant site in terms of coverage. So coverage tells you what is the amount adsorbed, loading, amount adsorbed per gram divided by what is the maximum possible amount that can be absorbed. So that is called as coverage. So if you do 1 minus theta, that's like how much surface is available for adsorption to occur. So that's like a fraction of vacant site. So now if we write the rate of adsorption, so dq by dt, rate at which the loading increases, so there will be a forward reaction between the adsorbent on the gas phase and the vacant site, and then there will be a reverse reaction, desorption minus, so kd into the what is loaded onto the material, or we can think about this as the sites where the material is present. So if you look at steady state, that's when the equilibrium is reached. So then we can write the equilibrium constant in terms of the forward and backward reaction rates, and then we can rearrange this expression to give you theta as kp divided by 1 plus kp, and if we write theta in terms of q by q max or q max, I am writing short as q max, so q will be k qmp divided by 1 plus kp. This is like our adsorption phenomena that we had looked at in the kinetics course. What this tells you, so if you plot this kind of curve, so if you plot volume adsorbed at STP per unit mass of the adsorbent, so it could be volume at STP per gram of the adsorbent versus pressure, so Q is on the y-axis, P is on the x-axis, you see these kinds of curves. So you see this is very characteristic of the Langmuir kind of curve. If you see at low pressures, Kp is small, so denominator of that 1 is very large as compared to Kp, it can be neglected. So you will find that Q is proportional to P, it's like a linear adsorption, first order. If you see at high pressures, the denominator Kp term dominates, and then Q simply tends to become some constant number equal to Qm. So that Qm tells you what is the maximum possible amount that can be adsorbed. That was our Q max. And then at high P, at high pressures, this behaves like a zero order process. Q is independent of pressure. Q is just a constant value. and we need to find this capital K, the equilibrium constant or adsorption constant, and Qm, the maximum amount of adsorption experimentally. So if you take this expression, if you just invert, you will get 1 upon Q would be 1 divided by K Qm, 1 upon P plus 1 by Qm. So if you plot 1 by Q versus 1 by P, slope will be equal to 1 by K Qm and intercept will be 1 by Qm. So that straight line equation allows us to find out the values of K and Qm. Some other types of adsorption isotherm that you are aware of are called as Freundlich isotherm. So here Q is written as K P raised to 1 by N. So K and N are empirically fitted constant. They depend on the adsorbent and the amount and the solute which is getting adsorbed. So adsorbate and adsorbent, and they are also temperature dependent. So if you want to find K and N, you can just take log of this. So log Q would be log K plus 1 by N log P. So if you plot a graph between log Q versus log P, we will get slope as log K and intercept as 1 by N. Typically N value is between 1 to 5. So P is a fraction. So it is P raised to 1 by N. So P raised to a fraction which is smaller than 1. Sometimes sometimes some other adsorption isotherm that people have proposed are a combination of Langmuir and Freundlich isotherm. So there you write Q as K Qm P raised to 1 by N divided by 1 plus K P raised to 1 by N. Or a Toth isotherm, Q is M P B plus P raised to T. Now you see the power is different in both these, in the numerator and denominator. So raised to 1 by T. So this is very less used. Freundlich, Langmuir and the modified Langmuir-Freundlich are used very commonly. One more type of adsorption isotherm which we will not study here, but just for your background information, what is called as a BET isotherm. So this is used to measure surface area of materials. What that does is you plot, this is an equation that is derived for this isotherm, again based on the assumption that multi-layer adsorption can occur. So if you see, P is the pressure at which adsorption is occurring, V is the volume of the adsorbed gas, P is the vapor pressure at a particular temperature. So if you plot this equation, if you plot P divided by V into P naught minus P versus P by P naught, you will get slope C minus 1 divided by Vm into C, and intercept will be 1 by Vm into C, where C is a constant that is related to what is the heat of condensation, that means latent heat of condensation, and the heat of adsorption. So this difference it gives you a value of C, and Vm tells you what is the volume of monolayer adsorbed gas. So what you try to work out from this equation, you measure the adsorption pressure and the amount that is adsorbed in terms of the volume. So if you plot this as a y-axis versus this as a x-axis, you will get slope and intercept. So from intercept you can work out what is the Vm, what is the volume of the monolayer adsorption of the gas. So from this volume you can now work out the surface area. So for example, if you find out volume divided by volume at STP, so that's 22.414, that tells you how many moles are adsorbed in the unimolecular layer, multiplied by Avogadro number tells you what is the surface, what is the number of molecules adsorbed, multiplied by area occupied per molecule would be the total surface area of this material, and if we do this per unit mass of the adsorbent, then we can calculate the surface area per unit mass. And again recall that surface area occupied by one molecule is related to the diameter, and then diameter you can relate it to the molecular weight. We have seen all this when we try to look at the membrane separations. So these are the different isotherms that are used. Sometimes to check whether adsorption is favorable or not favorable, something called as the separation factor is defined. So if you think in terms of the Langmuir isotherm, separation factor is defined as 1 divided by 1 plus KQm. If we write the Langmuir adsorption isotherm in terms of RL, right? So if you write this Langmuir isotherm in terms of this RL, you will find that Q by Qm is equal to this 1 minus RL into P divided by RL Qm 1 minus RL into P. Now try to derive this expression, don't just take this for granted, use this use this definition and you can easily derive this expression. So now if you plot Q by Qm versus P for different RL values, this is what you will typically see. So let's say Qm is some value, say 1. So if you say Q by Qm versus P, you will find for different RL values the adsorption isotherm behaves like this. So if RL is 0.1, the adsorption isotherm behaves like this. If RL is 0.95, the adsorption isotherm behaves like this, which means lower the Rm, more favorable is the adsorption on the surface. So RL indicates what is the favorability and shape of the isotherm. So as we said, RL less than 1 tells you favorable isotherm, RL greater than 1 or closer it is to 1, it is more and more unfavorable adsorption. We will take some problems now for solving. So we are going to start looking at problems on adsorption isotherms and how to calculate these adsorption isotherms. So just for refreshing your memory, we have seen Langmuir isotherm, we have seen Freundlich isotherm, combination, Toth isotherm, BET. We are not going to see this in this session. So we are going to start looking at problems on adsorption isotherms and how to calculate these adsorption isotherms. So just for refreshing your memory, we have seen Langmuir isotherm, we have seen Freundlich isotherm, combination, Toth isotherm, BET. We are not going to see this in this session, under this syllabus. Separation factor we defined. So here is a problem. So these some of these problems are from Cedar's book. You can look at the book and you can look at the problems as well. So let's say data of adsorption of pure methane gas on activated carbon is shown below. So the Q tells you how many centimeter cube of methane gas measured at STP adsorbed per gram of carbon. Right? These are the data of Q versus the pressure of the methane in the gas phase in terms of psi absolute. These are the values. Okay. So what I would like you to calculate is which isotherm, Langmuir or Freundlich, fits this data. So look at the previous video on types of isotherms and how to calculate the parameters for each of them. So you can pause this video, try doing this problem now. What I would like you to calculate is what is the R square value if you try to fit the Langmuir isotherm, what is the value of the equilibrium constant K, what is the value of Qm. If you try to fit a Freundlich isotherm, what is the R square value, what is the K, what is the value of N. Okay, so try to doing this yourself. Pause the video. Once you are done with the solution, you can proceed to check your solution. So if you want to fit Langmuir isotherm, recall that if you want to fit Langmuir isotherm, we plot 1 by Q versus 1 by P. So this is the data of what is plotted, 1 by Q on the y-axis versus 1 by P on the x-axis, and you can see these are the data points. And if you try to fit a straight line through this, you see that R square is very good, 0.9998, right? This is the slope and the intercept. Recall what the slope and intercept means. Our intercept was 1 by Qm. So 1 by Qm is 0.007256 here. So that means Qn will be reciprocal of this. It will be 137.82 centimeter cube of methane gets adsorbed, centimeter cube measured under STP condition per gram of the adsorbent. Slope. What does slope mean? Slope means 1 by KQm. So then you will find that K, if you work out from here, K would be 0.0123 psi inverse. If you want to fit Freundlich isotherm, what you do, plot log Q versus log P. So this is log Q plotted versus log P, and then you can see that this is a straight line fitted. The slope is here and intercept is here. R square is 0.924, not as good as Langmuir. Okay. But you remember that this data will have some experimental error, so don't expect R square to be 1. 0.9, 0.95 is very good. Intercept is ln K, so ln K is 2.794, so that means K is 16.35. Slope is 1 by N, so 1 by N is 0.3101, that means N is 3.225. So here you can see that clearly Langmuir is fitting better, but if you have lots of experimental data, then you will have lots of experimental data and there are some experimental errors, then this also is very good. Just a small thing to see is that although we are fitting a straight line, you see that there is a R square is good 0.924, but there is a systematic deviation here. This point is lower, these points are higher, and again these points are lower. That means there is a definite curvature to this data, which is not represented by a straight line. Because the data is over a small range, you can see that it fits a straight line and R square is good, but you see that there is a definite curvature, whereas there is no such curvature here. The fit is really good here. So in this case, for this particular problem, Langmuir fits better. Okay, you can take one more problem. So this is some data from a paper, isotherms for a dye adsorption on activated carbon of different sizes is given below from a paper. So what is plotted is X by M, this is nothing but Q. It is milligrams of the dye adsorbed per gram of the carbon versus the concentration of the dye solution in the concentration of dye in the solution, CE. Right? Again, you try to fit Langmuir and Freundlich isotherms for these different data. Now you will see that it also is going to be dependent on the size, because surface area may be different, porosity may be different for different types of carbon. So you will have the K and QM values different for different sizes. So recall from Langmuir isotherm, although we have seen it for a gas phase, Q is KQMP divided by 1 plus Kp. If we have a solution from which adsorption is happening, this P we would replace by C, the concentration in the solution, and Q would be amount X by M, amount adsorbed per mass of the adsorbent. Okay, so do this problem for yourself. Again, Freundlich and Langmuir isotherms. So the only difference is, in this particular case, data was given in a tabular form. Data here you have to extract from the figure. So there are a number of softwares that are there which allow you to import these images into the software and read data from these data points. So it allows you to easily interpolate or find out the values of the points corresponding to the data. So you can see for yourself how to do this. Okay, sometimes we would have a mixture of two components, mixture of two gases, let's say. Now again, if we write the forward rate constant, forward rate for the adsorption process, so there will be forward rate constant for A multiplied by pressure of A multiplied by the vacant sites. So vacant sites will be total sites minus what is which sites which are occupied by A minus sites which are occupied by B. And then the reverse reaction would be desorption rate constant multiplied by the sites which are having A present in them. So again, at equilibrium, the forward and the backward rates are equal, and then we can define Ka, capital Ka, as the adsorption equilibrium constant for A, and then you can rearrange these expressions. You will get Qa, amount adsorbed of A per divided by the maximum amount of A that can be absorbed, that is Qa underscore or subscript M. So QAM KAPA divided by 1 plus KAPA KBPB, and QB would be QM maximum amount I've absorbed for the B, KB PB divided by 1 plus KAPA plus KBPB. So in general, if you have multiple components, you can write this denominator as a summation of different K and the corresponding pressure. Sometimes this is modified to account for the non-Langmuir kind of adsorption. So you will see that you will have P raised to 1 by N, and then this N also is a dependent parameter depending on the type of adsorbent. Again, when there are multiple components, we can define selectivity of adsorption, just like we define separation factor, or just like we define relative volatility. You can define this as Qi by Qj, amount adsorbed for the ith component divided by amount adsorbed for the jth component, divided by the pressure of I and J in the gas phase. Now if you rearrange, you can find that you can write in terms of the Qm maximum amounts for I and J and the corresponding pressures, and if the pressures are small, then you see that it is just the ratio of Qm and K for the ith component divided by Qm and K for the jth component. Here is a small problem based on that. So for example, there are two components, let's say methane and carbon monoxide, let's say A and B, and the following data is available for the from the Langmuir isotherm for pure components. So for methane, QM is pure methane, QM is 133.4. For pure carbon monoxide, QM is 126.1. K for methane is 0.0137. K for carbon monoxide is 0.00624. Now use this data to predict the amount adsorbed of methane and carbon monoxide when the equilibrium gas mixture contains 70 mole% methane and rest 30 mole% carbon monoxide at a total pressure of 360 psi. And then you can also calculate the selectivity. So again, use these expressions and try to calculate for yourself. Pause the video and do the problem yourself. Okay, now that if you have done the problem, you can go forward and check your answers. So for example, if you are using multi-component equation, Qi would be Qmi Ki Pj, sorry, this should be Pi divided by 1 plus summation j Kj Pj. This is Pi, not Pj, so make that correction. So if we are writing I as methane, so Q for methane would be QMI, so that is QMI is 133.4, QM for methane multiplied by K for methane 0.0137 multiplied by pressure 0.7 times 360, so this is partial pressure of methane divided by 1 plus 0.0137 multiplied by partial pressure for methane plus 0.00624 multiplied by partial pressure of carbon monoxide. And same way for carbon monoxide you can write, and you will find that the Q for methane is 89.84, Q for carbon monoxide is 16.58. Now selectivity if you want to write, or separation factor if you want to write for methane over carbon monoxide, it will be 89.84 divided by 16.58 divided by their ratios of their partial pressure, 0.7 into 360 divided by 0.3 into 360. You will find that this ratio is 2.32, separation factor is 2.32. So these are some of the problems related to adsorption isotherms. Okay, now we are going to look at some of the kinetic aspects of adsorption. So for example, if you think about it, this is some data from a paper. So if you want to measure kinetics of adsorption, what you would do is you would take the solution inside. Let's say we are talking about the adsorption from a solution. We will take the solution, we will put the adsorbent, we will keep them at some particular temperature at which we want to measure the adsorption isotherm. So we know the amount of solution we have taken, we know the initial concentration, and we know the amount of adsorbent that we have taken. So M is the mass of the adsorbent, V is the volume of solution, C is the initial, C initial is the initial concentration. Now we start studying them together, and if we take out samples as a function of time, so the whatever is the solute that is getting adsorbed, it will deplete from the solution and it will go into the adsorbed phase, into the solid phase. So if we take out samples with respect to time from the solution, what we will measure is the concentration inside the solution at any point of time t. So you can plot this graph now, how the concentration inside the solution changes with respect to time. So let's say 0 time, this is our initial solution, initial concentration in the solution, and with respect to time, how the initial concentration changes with respect to how the concentration of the solute changes from the initial value to the final value. And these are for different adsorbents. This is actually data from a paper, and if you see that at very long time the solution, the concentration in the solution does not change, so that is the concentration in equilibrium with this solution. So if we allow this equilibrium to take place, then the amount adsorbed would be the volume of the solution multiplied by the initial concentration minus the equilibrium concentration, that means at very long time, divided by the mass of the material. So from this experiment we are going to get how the concentration is changing from the initial value to a value at which equilibrium is established, and this, once that equilibrium is established, the concentration in the solution is the concentration at equilibrium, and we can calculate the equilibrium value from here. So the QE versus CE data that we get from one such curve is actually 1 point on the adsorption isotherm, right? So if you take, let's say for example, XAD7 as an adsorbent, the concentration as a function of time changes like this. So what we get is at equilibrium after a very long time, this concentration is what remains in the solution at equilibrium. This difference multiplied by the volume is what has gone onto the adsorbent material divided by M. tells you how much is the adsorbed amount per unit mass of the adsorbent. So this experiment for one particular adsorbent, one particular temperature, we are going to get one data point on the adsorption isotherm. So this QE and CE are one data point on the adsorption isotherm. So if you take Q versus C, this will be the CE value and this will be the QE value which we get from this formula. So this is one point on the adsorption isotherm. Like this, we'll have to do experiments with different initial concentrations, different volumes, different mass, and again allow equilibrium to take place, and then we will be able to trace out this whole adsorption isotherm. Recall that, or remember, or look at important point to remember is this QE is different from QM. QM is the maximum amount that the adsorbent can adsorb. That happens at very, very large value of concentration. So as CE tends to infinity, this QE is the QM value. So 1 point and is going to give us 1 curve of concentration versus time is going to give us 1 point on the adsorption isotherm, and we'll have to get these several curves. Now these are curves for different adsorbents, so don't take them and plot them together. For the same adsorbent, we'll have to repeat this experiment several times and then generate this whole curve. Okay, so the data of how this concentration changes with respect to time, that tells you the kinetics of adsorption. And now let's try to think about what are the different kinds of kinetics. So for example, you could have a first order kinetics. So dq by dt would be k1, first order rate constant, multiplied by QE minus Q. QE minus Q just tells you what is the driving force for adsorption. So if you rearrange this expression, you will get ln QE minus Q would be equal to ln QE minus k1t. So if you plot ln QE minus Q on the y-axis versus t, you will get the intercept and you will get the slope. If adsorption follows second order kinetics, then dq by dt would be k2 QE minus Q the whole square. Now we can integrate and rearrange this expression. We will get 1 by Q is equal to 1 by QE plus 1 by K2, the second order rate constant, QE square divided into 1 by T. So if you plot 1 by Q versus 1 by T, we will get this as the intercept. QE will tell us the intercept and the slope will tell us the QE and the K2 value. So derive these equations for yourself, derive the linearized form for yourself, derive from this equation, derive the linearized form for yourself. There is a Weber diffusion model which says that you remember that diffusion length is proportional to square root T. So this amount diffused or amount adsorbed can be written in terms of Kd T raised to half plus I. So if the kinetics follow this model, then if you plot Q versus T raised to half, then you will get slope as Kd and intercept as I. Again, you might have studied diffusion with respect to time, and then you would have studied different models. So one of the model is Boyd's diffusivity model, which says that minus ln 1 minus Q by QE square is related to time, and this is purely a diffusional process. So the slope tells you what is the diffusivity of the solute inside the adsorbent. What we will do is we will take a problem for explaining or problem for helping us to do all these things. So for example, there are 6 sets of data for adsorption of a dye from aqueous solution. They are given here. So the data is given in terms of the concentration in the liquid phase in terms of milligrams per liter. This is concentration in the liquid phase in terms of milligrams per liter for set 1, set 2, set 3 and so on and so forth, for different loadings of the adsorbent as a function of time. So for example, set 1 means 0.3 liters of solution, 15 grams of adsorbent. Set 4 means 1 liter of solution, 15 grams of adsorbent. And you see at time 0, this is the initial concentration. So if you recall our discussion, one set of data is going to give you 1 point on the adsorption isotherm. So what I want you to do is fit an isotherm based on for this data and also fit kinetics of adsorption. So do this problem for yourself, don't go forward till you solve this problem. Once you have solved, then you can go forward for checking your solution. Okay, so here is the solution. So if you want to plot isotherm, what we are going to say, okay, let's assume that equilibrium is reached after 90 minutes. That means this data point is at equilibrium. So for this particular set, 51.6 is the concentration in the solution at equilibrium. For set 2, 24.94 is the concentration in the solution at equilibrium, and so on and so forth. So these are going to give us the CE values. Recall, these are going to give us the CE values. Okay, so you can put them here. Now QE values, so this is at equilibrium, what has remained in the solution. So 100 minus 51.6, that is the change in concentration multiplied by 0.3 liters. That will tell you how many milligrams have gone to the adsorbent, divided by 15 will tell you what is the loading Q. So recall this formula. Q is going to, QE at equilibrium is going to come from this formula. Okay, so you can populate this table now for set 1, set 2, set 2, set 3 and so on and so forth. So now that you have CE and QE values, you can fit an isotherm between the QE and CE values and find isotherm parameters and R square value for the fit. So again, if you have not done the problem, do it now. Pause the video, do it now. Here is what you will get. The CE values are like this: 51.6, 21.94, 18.96 and so on and so forth. Here 51.6, 24, 18, 10, 5, 2. The corresponding QE values we can calculate. They are written here. Okay. Now you can fit an isotherm between this QE and CE value. This is a very similar exercise to what we have done in the problem 1. And then once you do that, you can check whether the Langmuir fits better or the Freundlich isotherm fits better. Now if you want to find kinetics, what you need to do is calculate for each set what is the Q value as a function of time. Right? You remember how the Q value is calculated? Q at any time t is calculated from V, volume of solution, initial minus the concentration at any point of time t, divided by the mass of adsorbent. So for example, if you want to find for set 3, let's say you can find volume is 1 liter, initial concentration is 30, at any time t, let's say at 10 minutes, concentration is 20.27. So 30 minus 20.27 is what has gone into the adsorbent, multiplied by 1, that tells you how many milligrams have gone into adsorbent, divided by 15 gram, that tells you how many milligrams are adsorbed per gram. That's the Q value at this point of time. So complete this table for each set. Okay, pause the video, do it for yourself. Once you have this, then you have Q as a function of time. Now you need to fit different kinetics, first order kinetics, second order kinetics and so on and so forth. So pause the video, do it for yourself. If you have not done so, just pause and do it yourself. Once you do, you can check your values from the solution afterwards now. And then once you complete, you will get the fitted parameters for first order, second order, Weber model, Boyd model and so on and so forth for different sets of data. And then you will need to identify what is the best model across all sets of data. So if you have not done it, you need some help. This is how you would do. Let's say we take for example set 3. So you will get 0 to 90, that's the time, and the Q values for each of these time points for this set. So we need to fit different models, first order, second order and so on and so forth for this Q versus this T. Okay. So again, so if you want to fit first order, what you need to do is plot ln QE minus Q versus T. If you want to fit second order, you need to do 1 by Q versus 1 by T. If you want to do Weber model, you need to plot Q versus T raised to half. If you want to find, if you want to fit Boyd's diffusivity model, you need to fit minus ln 1 minus Q by QE square versus time. So do this for yourself for let's say set 3, and you can do it for other sets as well. If you need some help, this is what is the solution for set 3. So for example, if we to this data set 3 we fit a first order kinetics, you will find R square is 0.756, very poor, and the fitted value of QE is actually very different from the actual value of QE. So fitted value of QE is 0.269. Where are we going to get that from? That we are going to get from intercept, right? But the actual QE value we already have. For set 3 it is 0.736, right? So you see that first order fit gives you a very different value of the fitted QE. Obviously the fit is very bad. If you take second order fit, the fitted QE, again it is coming from slope and intercept, the rate constant and the fitted QE. These are coming from fitted values from 1 by Q versus 1 by T. R square is 0.867, very good fit. Because the data will have inherent some experimental error. So R square even 0.9 is good. If you want to fit Weber model, you are going to plot Q versus T raised to half. You will find R square is 0.811, much worse than this. If you want to fit Boyd diffusivity model, again you can find the fitted QE value is 0.713. Now this is agrees very well with the experimental value 0.736, and R square is 0.831, and then you can work out diffusivity of this solute in the adsorbent. That will come to be 7.03 into 10 raised to minus 9 meters square per second. So do these calculations for yourself, check that you get these answers, and then do it for other sets. It's a good idea that you do all these fitting exercise in Excel or something like that, and then you can identify which model works best across all sets of data. Here is one more problem. So let's say it is proposed to reduce the concentration of a dye using an adsorbent. The isotherm for this dye on the adsorbent is given by Langmuir isotherm with Qm equal to 100 milligrams per gram and K is equal to 0.02 liter per milligram. Calculate the amount of adsorbent required per liter of aqueous solution to reduce the dye concentration from 500 milligram per liter to 10 milligrams per liter. So do this solution yourself. You might have done some similar problems like this in your undergraduate course. Once you do this, you can check for yourselves. Okay, so remember what we are going to do is a single stage adsorption. Solution comes in with initial concentration or inlet concentration of 500 milligram per liter. Adsorbent comes in. No, it does not have any adsorbed solute here. We allow equilibrium to take place and the adsorbent will be in equilibrium with the solution leaving. Solution leaving, we want 10 milligrams per liter. So this will be the QE value corresponding to this equilibrium, corresponding to the Langmuir. So if you take Langmuir isotherm, Qm is 100, K is 0.02 into C is 10 divided by 1 plus 0.02 into 10. That will tell you QE would be 16.67. So corresponding to this CE, QE would be 16.67. Now we can do material balance. 1 liter of solution multiplied by 500 minus 10, that's how much milligrams have gone from the solution. They must be adsorbed into a mass M. So it would be 16.67 minus 0. That will tell you mass as 29.39 grams. That means per liter of the adsorbent, per liter of the solution, we need to put 29.39 grams of the adsorbent. So this is very similar to our undergraduate course. Recall, we used to do slope. This is the initial value, this is the equilibrium value because we are looking at one equilibrium stage, and the slope is liters of solution per gram of adsorbent, and then we can calculate this number. The mass balance is what we have calculated. You want to write it graphically, you can write this as well. So revise your co-current, cross-current, counter-current methodology for doing adsorption. So if you do cross-current in 3 stages, 4 stages, you can reduce the value substantially using the same amount split up into different parts. If you do counter current, the same amount put counter currently can give you very low concentration in the effluent. So the next part will be to look at ion exchange.